look at that. It is recording. Okay, let's look at number 4. And I really strongly suggest that you use pencil, because that will allow you to clear the board again and to go back if needs be. Okay, so I'm looking at number 4, things that I notice. Well, I do notice that there's a hydroxide here, but it doesn't exist here. So I'm not going to try to balance hydroxide. So that's off the picture. I don't have any single atoms, and I don't have any diatomic atoms. So they're off the thing. Yes. I'm looking for one on here. I don't see one on here. But like H2 or O2. Okay, are sealed. Any of those ones that we go through our list of elements, those ones. So diatomics are nitrogen, oxygen, fluorine, chlorine, bromine, iodine. Those ones are, and hydrogen. Okay, you see the big upside down L? Nitrogen, oxygen, fluorine, chlorine, bromine, iodine. Big upside down L on this side, and way over there hydrogen. Those are all diatomics. But you'll see it. What I do notice, though, is this guy here, the water. So what I'm going to do is, because water's present, I'm going to leave him to the end. After that, everything is fair game. Okay, so what I'm going to look at? Well, I'm going to look at the calciums then. I look at this calcium here, and I say there's one calcium here, and there's one calcium here. Oh, what do you know? Already balanced. So I'm going to put a dot on, just so that I don't keep going back to the calcium. Next one over, carbon. I've got 2 carbons here, 2 carbons here. What do you know? They're balanced as well. What's left? Only the oxygens and the hydrogens. So I'm going to key on the oxygens. I look over here, I say I've got 1 oxygen here, but I've got 2 here. Okay? So how am I going to change that? I have to put a 2 here. So now the oxygens are balanced, and all I've got to do is look at the hydrogens. Well, hydrogens. On this side, I've got 2 times 2 is 4 hydrogens on this side. How many do I have over here? I've got 2 times 1 is 2 hydrogens here, and I've got 2 times 1 is 2 hydrogens here, for a grand total of 4 hydrogens. It's balanced. Okay? Last step. Wait a minute, you're looking confused. Are you okay? You good? Okay. So the last step you do before you go on to number 5 is you just shake your head and clear it. One calcium, 1 calcium, 2 carbon, 2 carbon, 4 hydrogen, 2 4 hydrogen, 2 oxygen, 2 oxygen. There we go. In this one here, students that have come to me, I said, okay, look, for the purpose of this course, let's not look at that one. It's somewhat easily solved, but I don't want to even interject a little tiny bit of confusion. So my advice is, let's not do number 5. What you would do here in examining this is, this is in the way. Just in examining this, if you were assigned something like this, you would look at here and you say, well, I've got a nitrate here, and I've got nitrates here. Can I balance these? And the answer is no, because NO2 exists here. In other words, in order to get this NO2, 1 or more of these nitrates have to split apart. You can only balance polyatomic ions if they exist on both sides as they are. Not if they split apart. If they break down, you can't do that. Then you would have to go after the nitrogens in each case. Okay? So Barring that, then you'd say, okay, well, what do I balance? Well, you're going to leave, because it's water, you're going to leave water to the end, okay? Including the oxygens, because the oxygens is what you're going to go after. Oxygens live here, they live here, they live here, they live here. So what's left to balance? The nitrogens and the carbons. So you'd go after the nitrogens first. You've got 1 and 2 for a total of 3. So that means you'd put a 3 there and you'd start. I'm not going to finish it for you though. But that's how you start. You need to look to see what's available, follow the guidelines. Okay? Let's look for, it turns out that all of these, because they've got ammoniums and it splits apart, they're in the same boat. Okay? Let's do one of them anyway. See how far we can get. So here we go. We've got water, so I'm going to do water last. He's going to be last. What do I have to deal with? I've got nitrogens, chlorines, and calciums. So I've got 1 nitrogen here, 1 nitrogen here. At this point, this looks to be balanced, but I'm not positive. Next one over. Leaving the hydrogens because it's part of the water. Chlorine. 1 chlorine here, 2 chlorines here. See what I mean? See what I mean? I have to put a 2 there to balance these chlorines. But that means now I've got 2 nitrogens here and 1 here. So now I'm going to put a 2 there. So now at this point, chlorines are balanced. 2 here, 2 here. 2 nitrogens, 2 nitrogens. So I'm going to move on to the next one. I've got 1 calcium here and 1 calcium here. So those look to be balanced. What do I have left? Only the oxygens and the hydrogen. How many oxygens do I have here? I have 2. So I'm going to just write down a little 2 so I don't get lost. How many do I have here? 1. So I'm going to put a 2 here to balance the oxygen. So I'm going to put a little dot here. I'm going to put a little dot here. And the only thing that's left is hydrogens. Now this is going to take some, and you've got to be really careful of this step, because hydrogens live in a number of locations. Over on this side, you have got 2 times 4 is 8 hydrogens here. You've got 2 times 1 is 2 hydrogens there, for a grand total of 10 hydrogens there. So I'm going to put a little bracket here so we're following along that this is the total number of hydrogens on the reactant side. What about this side? Well, I've got 2 times 3 is 6 hydrogens there. I've got 2 times 2 is 4 hydrogens there, for a grand total of 10 hydrogens total. Guess what? It balances. Do you see how it follows that if I go after the oxygens, the hydrogens just follow along? Yes, Ms. Anderson? Sure, let's, oh, that's really foggy. Okay, are we good now? You've got to put your name on the board. Okay, are we good? Let's look at the next one. What do you notice about number 7? What things do you notice about number 7? Yes, dear. Say again? No, we're on this one here, 1-7. What do you notice about the four? Yes.
It's like almost the exact same as 6.
In some ways, yes, it's very similar to 6. Yeah. What do you notice about, but apart from that, what do you notice about the things we're dealing with? Yes, Ms. Anderson.
On the left side, it has 2 polyatomic ions.
Mm-hmm.
Plus different elements and
Mm-hmm. Let's look at, okay, other things that I know, like I know, so I look at this and I say, okay, well, on this side, I do have a polyatomic ion in ammonium ion, but it splits apart. So even though this is a polyion, it doesn't exist in the same form on both sides. So I can't balance him as if he was a single atom. But I go over to the next one. I find that I've got a sulfate here and a sulfate here, and they exist in no other place. So those guys, the sulfates, I can balance like they're one atom. Okay? What else do we notice about this? I have a water. Yes, sir. Oh, we will. But the things that we're looking for, when we start every balancing of equation is, are there diatomics? Are there single atoms? Are there polyatomic ions that exist on both sides in their form, undivided? And does this thing have water? So those are the 4 things you look at. Everything else falls under everything else. But those are the key things that you want to look for, because they're going to tell you which things to do first and which things to do last. So did you know you have a starting point? See, for me, the danger for Pat Hayden is that he goes in here and he just starts willy-nilly going back and forth, and I could end up trying to balance oxygens before I even balance the calciums. That would be a mistake. Huge mistake. So what do I do know this? The only thing that I've actually got, these 2 things here, this and this, these are the 2 hints that I'm dealing with. The sulfates on both sides and the water. So this is going to be last. This I can balance anytime. And that's about it. So what do? I start at the beginning. And I can't balance the NH4, so I have to balance the N. So how many N's do I have? On this side, I have 2, because this 2 here tells me I've got 2 total ammonium ions. Each one has 1 nitrogen, so 2 times 1 is 2. Over here, I've only got 1, right? So I'm going to put a 2. Okay? I'm leaving the hydrogens and the oxygens to the end. So now I'm going to go over, I'm going to balance whatever's next. I have a sulfate ion here, 1 sulfate ion here. Oh, wait a minute. I forgot to put a dot over the end, on both ends. So now I'm going to go over to the sulfate ion. I say I've got 1 sulfate ion here and 1 sulfate ion here. Okay, these guys are both balanced. I move on. Next one. I've got 1 calcium here and 1 calcium here. Guess what? He's balanced. What's left? That's right, hydrogen oxygen. And what am I going to key on? The oxygen. I'm going after the oxygen. So I'm going to look, now, because I've balanced the sulfates, when I'm talking about the oxygens, I ignore those because they're already balanced either side. So now the oxygens that are in play are the oxygens here and the oxygens here. How many oxygens do I have here?
1.
2. 2 times 1 is 2. How many oxygens do I have here? 1. So what am I going to do? Put a 2 here. Okay? So now this oxygen and this oxygen are balanced. Only thing that's left, hydrogens. Again, I got to be careful because hydrogens live in a number of different locations. So let's go back to here. How many hydrogens do I have here? 8. 2 times 4 is 8. How many here? 2. 2 times 1 is 2. So total on the reactant side is 10. Now I'm going to go over here. How many hydrogens here? 6. 2 times 3 is 6. 2 times 2 is 4. It's balanced. And again, I am not going to go on until I clear my head and justify the atoms. So, 2 nitrogens here, 2 nitrogens here, 4 hydrogens plus 2, 4 times 2 is 8, plus 2 is 10 hydrogens here, 6 and 4 is 10 hydrogens here. 1 sulfate here, 1 sulfate here, 1 calcium here, 1 calcium here. Bob is your uncle. Yep. Both those are right. Okay. When I'm looking at number 8, what stands out as, oh my goodness, I can do this? Yes, dear?
There's NO3 on the side.
Thank you. You have nitrates existing as polyatomic ions on both sides and without being split apart. So this is what you're looking at here, and this is what you're looking at here. That means I can balance them as if they're one atom. How many nitrates do I have on this side? 2. How many nitrates do I have on this side? What am I going to do? 2 in front of the silver nitrate. So now, this is balanced, and this is balanced. Moving along. How many silvers do I have? 2. How many do I have over here? What am I going to do? Put a 2. So now, these silvers are balanced. Moving along. How many coppers here? 1. How many coppers here? 1. Already balanced. Okay, moving along. How many chlorines do I have here?
2.
How many chlorines do I have here? 2. 2 times this. I have 2 here, 2 here. It's balanced. 2 silvers, 2 silvers, 2 nitrates, 2 nitrates, 1 copper, 1 copper, 2 chlorides, 2 chlorides. Bob's your uncle. Just like that. Okay, I want you to do the next one. I'm going to give you 2 minutes. Oh, shut up. Oh, I'm talking to my computer, not you. Okay. What do we notice? We notice that there are actually two different polyatomic ions that exist in our whole forms on both sides. We have the ammonium ion and we have the carbonate ion. So this guy is going to be like falling off a log easy. So why don't we start with them? Seems reasonable. One ammonium here, two ammoniums here. One ammonium here, two. One carbonate here, one carbonate here. Those are balanced. Those are balanced, and those are balanced. This is too easy. I should be going home now. What's left? Barium and chloride. One barium here, one barium here. Done. Two chlorines here, two chlorines here. Done. That was too easy. Do the next one. Okay, fine. Oh, you got it. Okay. Cool. You guys are getting too fast, man. This is, we only got 1 minute. Has everybody finished?
No.
Not yet? Well, if you guys get that fast, I'm going to have to think of something really nasty. I don't know.
There's an order on how to do it. I have it and I wanted to write down the order. Is it polyatomics and then
Well, it's you don't have to do either thing first or second. There's just some strategies that are best practices. So you tend to leave individual atoms or diatomics to the end. If you've got water involved, leave it to the end. If you've got polyatomic ions that exist in both sides, then you deal with them as if they're one atom, but that's about it. The rest is just, it's loose. You can go either way you want.
to me it looked like it was almost easier to do polyatomics first though.
Well, that's fine. You can do the polyatomics first.
Maybe just
Doesn't matter. As long as you've got polyatomics that exist on both sides, you can deal with them as if they're single atoms. That's all. So here we go. This is probably the easiest of them all. Nice way to end off. Things that you notice, a lot. There's a lot that you notice here. First of all, that you have sulfates that exist on both sides in their entirety. That's a good thing. The second thing is that two of the entries are elements, so they can be left to the end. So, like Josh just suggested, probably easiest this way to balance the sulfates first, and he's quite right. I've got 3 sulfates here, 1 here, out of 3. So now, The sulfates are dealt with. Only thing left here are the atoms, in fact. So I've got 3 copper here, and now I've got 3 copper here. I've got 2 irons here. Now I have 2 irons there. Yeah, it's. I think one of the things that I've noticed in past grade 10 classes is that even though it's the pure fact that this is new stuff, students automatically shut down. And they say, I can't do that. Oh no, you can do that. If it makes you feel any better, about 12 years ago, I was teaching Chemistry 11. And one of the guys in my class was friends with the chemistry teacher at RSS. And he showed me this equation that actually could only be solved, are you ready for this? Algebraically. It took 2 pages of calculations in order to solve this equation. So he showed it to me. I remember it like yesterday. I felt so stupid. Because I went through it and I thought, okay, I get it. I can do this. So I gave the sheet back to Travis, and he gave it back to his friend, the chemistry teacher. I tried to do that for 3 days. I never did solve it. So if it makes you feel any better, welcome to my world. You know, it's that kind of thing. Okay, page 5. I never did solve that thing. It was horrible. It was like seriously horrible.
What was the equation?
Oh, I have no idea. It was like this long, and I'll bet you there's probably seven entries on each side. What the problem was that there was such a degree of interchange that if you changed 1 on this side, you changed 3 on this side. And you know if you change 3 on this side, you've probably changed 4 on that side. And it was like, that's why it could only be solved algebraically. I know. Travis was not my favorite student for about 4 weeks after that. It was like, okay. What we want to do now is we want to talk about chemical reactions and predict, in real sense, we need to be able to predict, to identify the kind of reaction that is taking place, and then ultimately to predict what's going to happen. That is where we're going now. So I want you to imagine that we have a bucket full of different kinds of atoms. And my suggestion here is just to help you in the process. I would go and I would just highlight all the positive ions one color and all the negative ions another color. So I'm going to do positive ions yellow because I can. I think I'm going to use green. You can use whatever color you want. I don't really care. I like green because I'm Irish. Oh, thank you, dear. See, I missed it. Okay, now my question to you would be, if you had a bucket, and I'm going to pretend that this is in solution, so these are all aqueous, which means that these ions are not locked in position, but they can move around. So if this was a solution of these containing these ions, what would you predict could happen? keeping in mind the laws of electrostatics. What are the laws of electrostatics? Dear. What repels each other? And what happens to the positives and negatives? They attract each other. So looking at this bucket full of ions, what should be in your mind is that, oh my goodness, how many different combinations could I come up with? Well, maybe not millions, but let's say I've got 5 positives and I've got 6 negatives. I'm thinking probably I could come up with 30 different combinations here. Okay? Now, the only thing that you have to be careful of is the combining capacity, right? This goes back to before, when we talked about the Hooke's, right? So, for example, if I said, let's just isolate, let's pretend that we're just going to talk about one positive and the rest of them the negative. Let's, iron's there. He's close. So, here we have, and we have, what do we have? We've got SO4 minus 2, we've got NO3 minus 1, we've got OH minus 1, we've got O minus 2, we've got N minus 3, and we've got Br minus 1. So you would be correct if you suggested that iron and sulfate can combine, right? Now for you guys, just reaching back into your bag of tricks from the last chapter, what would you end up with? Exactly. SO4, 3. So this guy here will meet in the middle. No, I'm not going to do that. I should do this in another color is what I should do. I'm going to do it Fe 2 SO4 3. Okay? Now, you guys, I'm not going to go through the whole thing, but you guys should be saying, okay, I predict that this is what's going to happen based on the fact that this is positive and this is negative, and it's going to combine in that ratio. This is what you're doing here is you're actually taking something that you learned in a previous chapter and you're applying it to this chapter. That's all you're doing. All right? So it's nothing really new. It's just using something you've already learned. Okay? Now, we want to spend some time talking about I think there's six different types of chemical reaction. Now for me, I'm going to have to use colors, and I suggest you use colors. I suggest you come up with 5 colors. I'm going to use my pencil crayons then. Okay, a synthesis. The first type of reaction is this one here. To synthesize something means to make something out of simpler parts. So, for example, I'm going to do 2 equations. The first equation is what we call a general equation. The second one is going to be an example. So in a synthesis, you take one thing and you combine it with something else, and it's going to produce something more complex. In this case, these are both elements. In a synthesis reaction, you have two elements that combine to form one compound. Classic example is this. Classic example is this. H2 plus O2 Now, I'm not worried about the fact that this is not balanced. I get that. I'm just trying to give you an example of how this works. Okay, so that's a classic example. We also did another example the other day where we burned magnesium. Remember, we burned the magnesium. Was that this class?
That was last one.
Okay. We burned magnesium ribbon in oxygen and produced magnesium oxide. Two elements, magnesium and the oxygen, combine to form magnesium oxide. Another example of a synthesis reaction. Okay? Are we okay with that? Dear? No, I know. I'm not worried about the balancing. Okay? I don't care about the balancing for this. If you want to put 2, that's fine. Okay? Okay, next, decomposition. You guys should know, have a sense, in English, decomposition is when something starts to rot and fall apart. Same thing is true in chemistry. Decomposition is the reverse process of synthesis. So it's where you take something that is complex and you break it down to two things that are simple. So you start with a compound and you end up with two elements. So you probably are ahead of me already because you guys are like totally amazing. And so this becomes A plus B. Oh, sorry, wrong color. Try again. A plus B. And let's use the same thing. I'm starting out with, oh, sorry, too high. I'm starting out with H2O, and it is decomposing into hydrogen and oxygen, and if you like, we will do put the 2's in there too, just to keep everybody happy. Okay? Simple. No big deal. You okay? Next up. Single replacement. All right. Single replacement, I don't know. This is a Christian school, so it probably has never happened here. But I didn't go to a Christian school. So we had school dances like every second week. Single replacement is like you've got a couple dancing and some guy cuts in. That's a single replacement. So it's like this. You have one element and a compound and you switch partners. Now the trick here, it has a bearing on the nature of the two elements in the compound. So it looks like this. I need it orange. Now I'm going to use green. Single replacement is where you have like A. Yes, thank you. You have like A plus B.
Can we hand this page in at the end?
No, this is your notes. And here comes, so here's the couple. Remember that this is going to have a positive charge on it because it's first. This is going to have a negative charge. And so if this is a metal, which is normal, what's going to happen is this guy is going to come in and say, excuse me, but may I cut in and the guy's going to say, I just got the answer for myself, you turkey. But he's going to be ejected. And so you're going to end up with A okay? So A comes in, kicks B out, like that. All right? Make sense? Okay, let me think. What can we use? I know. Classic example, a very expensive example, mind you, is if you take copper metal and you immerse a piece of copper in silver nitrate. Believe it or not, you will get copper coming in, kicking out the silver, producing, now this is where it starts to get really interesting. The predominant charge on this copper is going to be +2. The predominant charge, we know that silver is always +1, and this is -1. So when you predict the outcome, you have to take into account that switch. So this is going to produce this is a very cool demonstration, but like I said, it's really expensive.
Does that still say NO3 in the brackets?
Yes, it still says NO3 in the brackets. So what you can do, this is really, this is true. I've got some silver nitrate in there, but it costs like, for a little thing like this, a little jar like that, $30. Yeah, but what you do is if you take a piece of, just a wire, copper wire, and you put it in silver nitrate, what's going to happen is that you will see crystals of silver grow right on the copper. Right on the copper. And the water will turn blue. Beautiful blue like this, because copper in solution is blue. So copper nitrate will go blue. So it's a really spectacular, rather slow, but it's a really spectacular demonstration, but it's expensive like heck. It's expensive. But this is a classic example. Now, double replacement is, okay, imagine yourself, you're back at the school dance. And now in this case, you've got two couples. And they say, hey, how about we change partners? Okay. And they change partners. That's a double replacement. So, I'm going to need more colors here. I'm going to use, so it goes like this. AB plus see, that's an orange, by the way. CD. Now, you have to be really careful here, because you have to remember that this guy's going to be positive, this guy's going to be negative, this guy's going to be positive, this guy's going to be negative. And so when they combine, they have to combine positive and negative, positive and negative. So, what's going to happen? Yeah. So this guy's positive, this guy's negative. So the first thing is going to be that's orange, sorry. A, D, plus, what now? CB. Very good. You guys are rocking. CB. So my favorite demo for this is if I take lead nitrate, which is PB. Oh yeah, I can do this. We can do this next time. PB NO3 2, and I combine this with potassium iodide. So potassium iodide is just Ki. Both of these are very cheap, and they have an instantaneous and rather startling effect. And so what's going to happen is that PB is going to go with I. So you're going to get PB. Now this is plus 2, this is minus 1, this is plus 1, this is minus 1. So PB is going to have 2I and I2. It's going to be PB I2. And what's now? KNO3, right? K. Okay. Now this is really cool. Maybe we'll have to do it tomorrow. It's because it's 3 o'clock right now. Yeah, remember guys, got chapter test tomorrow? Yeah, everything comes due tomorrow. Yeah, so bring everything in. Thank you for putting up the chairs. Appreciate it muchly. Much to believe from in here. You okay with this? Come in and see me, okay? Or one of your unit teams. We do this, okay? That's why. Oh, snap. I did it again.